Okay, so we're ready to talk about electric fields. Electric fields are very important in being able to understand what's happening around charged objects. One of the technologies that I highlight in class is electrospinning, actually using electric fields to weave these fibers together, these nanofibers. Electrorotation, electrostretching, we're talking about using electric fields in the biological realm. And biomedical engineering is going to be really critical in the future. So what we have around charges are, empty space that's filled with these electric fields. And so, there's these fields there regardless of what else is out there. You can have a positively charged object, negatively charged object. Let's say that's the only thing out there. You're still going to have these fields. And so, and these fields are there, and when other things come into those fields, they can be affected. And so the way that we define the direction of an electric field is that, if we place an object in there, it'll experience a force, and we base this based on a positive charge. And this is probably the most critical thing with the electric fields. We define the force per unit charge based on a positive point charge. And so if we have, a proton and we place that, next to a Van de Graaff generator, is positively charged. We place a little proton, which is smaller than this dot, right? Much, much smaller. We say, how would that be affected? And that's how we define the field. Fields are helpful because, forces only exist if there's two or more particles. But the fields exist no matter what. And so these fields are there, and they're ready to act if other things come into it. The field of only one particle can be calculated at a time, and we can figure that out. So let's say we have a positively charged object, right? Let's say we had that Van de Graaff generator. I want you to go ahead and draw a circle with these positively charged sphere, right? Something positively charged, again, just means that there's a lack of electrons. Let's say we placed a little proton right here. How would it be forced? Well, let's assume, this is, out in space, no force of gravity. This is going to go straight away, straight out. But let's say we place a little proton right here. What's going to happen to that? Well, it's going to go straight away. Let's say we place a little proton here. It's going to go straight away. Place a little proton here. It's going to go straight away. Place a proton here. Same thing, right? So here. So the number of field lines represent the strength of the field. So let's say this Van de Graaff generator became even more positively charged, right? Let's say it was very, very positively charged. Well, what we would do is we would draw more field lines to represent the stronger magnetic or the stronger electric field that's generated from this, right? The thicker those lines, the more lines that we have, the greater the amount of field that we're saying that there's there. So the key here with this, the field lines indicate the direction of the force on a positive charge. So that's how we determine the direction of the field. Now, those positive test charges aren't actually there, but if they were there, that's what would happen to them, and that's how we draw the electric field. Negative charge will have force in the opposite direction, right? So if we consider, a field around a negative charge, if we have little test charges here, right, at these different locations, they're all going to go inward. And so fields go into negatively charged objects, and fields go out of positively charged objects. Let's say we considered a field here. Let's say we had two charged plates. We have a positively charged plate, we have a negatively charged plate, and we want to find out the force on test charges that we place in here, and we can figure out what the field is. Well, it's pretty easy if we consider this going to infinity on this way, essentially infinity this way. Place the test charge here, it's just going to straight down. Place the test charge here, it's going to go straight down, right? Here, straight down. Here, straight down. Here, straight down. Here, straight down, right? Here, straight down. Now, as we get closer, what's going to happen is, let's say we place a test charge right here. This is going to kind of push it out. It's not going to push it straight down. It's going to push it out. And then this is going to come in here like this. And then if we have one right here, it's going to go straight out and then come around like this, right? So, yeah, depending on the way that the charged objects are set up, you can have different forces on them. How about this? Let's say we have a positively charged sphere on the left and a negatively charged sphere on the right, and we want to find out, what the field looks like between the two charges. We do the same thing. We place a positive test charge here, see where it goes, right? Place a positive test charge here, draw where it would go. So if you think about it, right, KQ1, Q2 over R squared, if you had a little proton here and you have this is going to have more influence on it because the radius is closer here than it is over here, right? KQ1, Q2 over R squared. So the force on this is going to have more influence. Now, as soon as it gets further away, this one's going to start to have more influence. It's going to pull it around like that. If we place one down here, it's going to be pulled around like that. Here, it's going to go straight up and then get pulled around like that. If we have one over here, this one will go straight away because this charge is always going to have more influence on it than this one. So again, these protons here, and it's kind of dangerous to draw it like this because these protons are so tiny, and they're test charges, right? They're actually not really there. They're just helping us draw the field. And we got one over here. Let's say we had two positively charged spheres. We wanted to find out what the field would do. And so what I want you to do here, go ahead and pause the clip and place some test charges there and see if you can draw where you think they might go. And then we'll see how you do. So go ahead and pause the clip, give this a try, and hit play when you're ready to check. All right, so we've got our test charge. Now, this one's going to force it away, right? This one's going to force it away, and then this one's going to have influence on it as well. It's going to head straight up. This one will be symmetric. This one will start to head this way, but then it's going to be forced down. This one will be forced up. This one will be forced over. This one is not going to be quite as forced by this one because it's going to stay further away. So this one still has more influence. This one may be down like that. So you got to kind of get the idea there. What if we had two negatively charged objects, right? We want to draw what the field is doing. So yeah, why don't you go ahead and try this one. What I do for my students in this one is I say, okay, what if you had test charges in all these spots? What's going to happen? And you can draw what you think will happen. So go ahead and pause the clip and give this a try. Draw where you think all these test charges would go. And when you're ready to check, you can hit play to continue. Okay, so we could try each of these, one at a time. Some are a little bit easier than others. The ones that are, flat across the horizontal here are pretty straightforward. We've got this one coming in, the other one coming in. These two would go straight out. These would get pulled down and in. These may get pulled. Well, we know they're definitely going to get pulled in here. They may get pulled actually more like this as they get pulled in, because they'll get pulled down by this one and over, likewise over here. So yeah, you should have had them kind of going in like that. Okay, so field vectors from the field lines, a given point. It's not the field itself, but we can determine by the field lines. So what we do is we can get the tangent. Let's say we have a positive charge here, a negative charge here, right? Let me redraw that. Positive charge here, negative charge here. Let's say this is the field line, right? And you want to get what the field is right at this spot right here. Well, it's curvy, right? So what you do is you take your tangent line where it only touches at one spot, and that is the field at that spot. It's the tangent line where it only touches at that spot. So that's the electric field, and that is a vector. The field line, right, this red line is not a vector itself, but if you get a tangent at any of those points, that's the actual field at that spot. All right, so if we want to take a look at now the force on a charge due to an electric field, we can do that. We have the electric field in newtons per coulomb. We have the charge in coulombs. and we want to find the force. And force is a vector quantity, and we have to have a direction with this, right? So we can do. All right, so let's say that we had a uniform field, 4,000 newtons per coulomb field pointed towards the north, and we want to find the force exerted on a 400 microgram styrofoam bead and has 600 excess electrons. Remember with a field, right, if you place a positive test charge there, you see where it goes. It would go this way. So this force would actually be downward like this against the field because it's negatively charged. So the first thing that you're going to need to do is figure out how much charge there is, how much Q there is. And then once you do that, you can figure out the force on it due to the field. And then you can use the second law to figure out what the acceleration will be. So, and actually on this one, I think I'm just having to get the force. Yeah, so you can calculate what the force should be. So go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. All right, so the total amount of charge, 9.6 times 10 to the negative 17th coulombs. That's because we have 600 of the elementary charges, so we'll multiply those two. Force equals E times Q, so we know the field, we have the charge, and so this will be the force on it, 3.84 times 10 to the negative 13th newtons to the south. All right, so let's consider this one. We have a proton traveling at 440 meters per second in the positive X direction. Enters a uniform field at a magnitude of 5,400 newtons per coulomb in the positive Y direction. We want to find out the acceleration of it. So here's the situation, right? We've got our positive charge entering the field, and it's being forced upward like this. And so, yeah, I'm going to see if you can figure that out. Go ahead and pause the clip and determine the force first. And then once you get the force, you can get the acceleration with Newton's second law. All right, so force is E times Q. The charge of a proton is 1.6 times 10 to the negative 19th. And we have the electric field, 5,400 newtons per coulomb. And that is the force on it, 8.64 times 10 to the negative 16th newtons to the north would be the force. So we can use F equals ma according to Newton's second law. We know the mass of a proton, and you have to look that up on the data booklet. And we know the force, and so to divide out, and that's going to be the acceleration of it as it goes. All right, so something important to remember is that for a spherical charge that's hollow inside, let's say, this is positively charged, it turns out that the field inside is actually 0. Anywhere inside here, there's no field. Now, as soon as you get outside, then you have a certain radius away, but inside there's no field.